All right, we're going to continue in lesson 4.4. We're talking about linear models and point slope form. So this is task 2, and it says model with linear functions. All right, so Jim has a long drive home from a conference. He notes that his odometer reads 1,500 miles at the beginning of his journey. Jim reaches home after 4 hours of driving. How can you model the mileage on his odometer as a function of driving time? Graph the function and identify any minimum or maximum values. All right, it says Jim drives an average speed of 50 miles per hour. Use a verbal model to write a function rule. All right, so we're going to say the mileage on your odometer. So odometer, or O of t, is going to be the name of our function. Average speed, 50 miles per hour. Driving time in hours is going to be t for time. And then plus your starting mileage. So he started at 1,500 miles was what was on his odometer when he began. So this, if you see, these just come down, and that's what makes your equation. O of t equals 50t plus 1,500. Why does it make sense for O of t to be a linear function? All right, Jim's odometer began at a constant value of 1,500. That doesn't make sense. That just means his odometer was at 1,500 when he started. It has nothing to do with being a constant value. But it says a constant rate is used to write the equation. So he's traveling at a constant rate of 50 miles per hour. So that second one is going to be the correct answer here. All right, it says graph the function. Identify a point on the graph of the function O. So they just plugged in 0 for t, 0 amount of time. And if you plug in 0 for time, 50 times 0 is 0 plus 1,500. So the odometer is going to read 1,500 when it starts. So that's your y-intercept. That's where it starts. So 0, 1,500 is on the graph of the function O. What does O of 0 represent? It represents the initial odometer reading, the initial speed. So the initial odometer reading is what the reading was when it first started. If you go back up here, you can see he notes that the odometer reads 1,500 miles at the beginning of his journey. So we can see that that matches exactly what that says, the initial odometer reading. All right, it says identify the slope of the function. All right, the slope is 50, and that's because he's traveling at 50 miles per hour. So you can see he has graphed this on the line, and that way he can see what his function looks like. It says, how does the slope help you sketch the graph? Well, 1,500 is going to be the y-intercept, and you know if you have a y-intercept, you can use the slope, the rise over run, to get to the next point. So that's what he's done. He's used the y-intercept and the slope to graph the equation. All right, it says select the word to complete the sentence. The function is increasing. So we can see that this function is going up. So the amount of time is increasing. As the amount of time passes, the number of miles is increasing at a rate of 50 miles per hour. All right, so it says the domain of the function is limited to the hours of Jim's drive home. The minimum number of miles on his odometer occurs at the beginning of his trip. So the minimum value of the function O is 1,500 miles. Since Jim reached home after 4 hours of driving, then O of 4 equals 1,700 miles, and that's a maximum value of O of t. So it says which statements are true. Select all that apply. All right, so the domain represents the amount of time when Jim was driving. The range represents the amount of time when Jim was driving. All right, so if you go back up here, you can see that your domain is always your x's. And you can see that 0, 1, 2, 3, that's the number of hours. So the domain is the amount of time that he has been driving. All right, that means this one can't be true. All right, it says the range represents all possible odometer readings while Jim was driving. All right, so the odometer is going to be the number of miles, and it's going to have the number of miles from the starting amount, 1,500, up to whenever he gets to the end of his trip, which here it says 1,700 miles, okay? So the range is all possible odometer readings. And then it says Jim drove 200 miles, Jim drove 1,700 miles. So he started at 1,500 miles, and he ends up at 1,700 miles. So the difference between 1,500 and 17 is 200 miles. So Jim actually drove 200 miles on his trip. All right, that's all for task 2. If you pause the video, we are going to start task 3. You can move to that if you want and work along with me. All right, we're going to look at task 3. Again, we're on lesson 4.4, linear models in point-slope form. All right, it says a model with linear functions. You can use the point-slope form of a linear function when you know the rate of change and some function value. Consider a line slope M that contains the point x and y from point 1 for some linear function f. The point-slope form of a linear equation is a direct consequence of the slope formula. All right, so if you know the slope formula, which we've worked with, that's your difference in y's over your difference in x's, and we usually use y2 minus y1 over x2 minus x1. If this one doesn't have a subscript and this one does have a subscript, it's the same thing. It's two separate points. So difference in y's over difference in x's. So that's your slope form or slope formula. And if you take and multiply both sides of your equation by the denominator here so that you don't have a fraction, then that gives you this new equation. So this is your point slope formula. Okay, so y minus y1 equals m times x minus x1 is your point slope formula. So you can use a point and your slope to actually write an equation. All right, so this is just showing that you have a point, x and y, and this is showing you have another point, x and y subscript 1. When the known point, x and y subscript 1, is the y-intercept, 0b, point-slope form can be rewritten to obtain the slope-intercept form. All right, so you've got the slope-intercept form here. You've got point-slope form here, and we're going to rewrite it into slope-intercept form. So if you look at these equations, you know we've looked at standard form, we're looking at point-slope form, we've looked at slope-intercept form. These are all just different equations to write a linear equation. So what they're saying is you can take this and plug in a point, your y-intercept, 0b. And if you look at the graph here, on this one it would be 0, 3 would be your y-intercept. And you could plug that in here and rewrite this very quickly as y equals mx plus b. All right. So let's look at this example. It says a bald eagle is shown diving toward its prey. Its distance from the ground is decreasing at an average rate of 140 feet per second during the dive. So you can see it started here, and after 0.7 seconds, it has went down 62 feet above the ground. Okay, so it says select the number to complete the sentence. The rate of change of the eagle's height above the ground is, well, it's negative because it's going down. So there's a negative rate of change when the graph goes down from left to right. All right, it says let t of 1 represent the time in seconds after h, t of 1 represents the height of the eagle in feet above the ground. What point can you determine from the given information? All right, so if you look at the given information, we've got the 0.7 seconds and we've got the 62 feet above the ground. So we know that that is a point on our graph. All right, it says the first step is shown for completing the conversion of point-slope form into slope-intercept form. All right, match the remaining step numbers to the equations. All right, so this is our y minus y1 equals m times x minus x1. So in this case, we're using time. That's our horizontal distance, time. That's our independent variable. And that's just a different variable than x, but it's still the same formula. Difference in y's equals slope times difference in x's. Okay? So what can we say step 2 is? Step 2 would be to take the 62 and the 0.7. That's the point that we had from above. X is 0.7, 62 is the y, and you can see that the y goes first. That's why the 62 is here. So that matches with that equation. Okay? And then step 3 is get rid of your parentheses. Use distributive property. So we're going to say that is step 2. And then the last thing is going to be to add the 62 to the other side and get h of t by itself. So if we add the 62 to the other side, that converts it to slope-intercept form. Okay? And you can see exactly they've plugged it in right here. If you need to look at that and work it out yourself, that can be a good way to figure that out. All right, it says the bald eagle's initial height was... All right, so from the equation, the y-intercept here is 160. So we know that that was the bald eagle's initial height. And that comes directly from plugging 0 into your equation and getting the 160. Or rewriting this in slope-intercept form, that will give you that as well. All right, so that is all for task 3. If you have any questions, please let me know. All right, lesson 4.4, we're going to continue with task 4. All right, it says model with linear functions. LaskMe adds the same amount of money into a savings account each week. After 8 weeks, a total of $576 have been saved. After 20 weeks, a total of $1,140 have been saved. Use the information in the table to find the initial amount in the savings account. All right, so we're given 2 points. Basically, our x is our time in weeks, and our y value is the savings, like the money, the amount in dollars in your savings account. All right, so if they graph those, and you can see that the scale goes from 2, 4, 6, 8. This is time in weeks across the bottom. And then 4, 8, 12. So that means each one of these is 200. So 200, 400, 600, 8, 1,000, etc. All right, so they've graphed the 2 points. And it says, why draw the line through the 2 points? All right, so if you draw the line through the 2 points, that shows you that it is a constant rate of change. So we have a linear equation because he is saving the same amount of money each week. Okay, saves the same amount of money each week. So that makes it linear. All right, it says use the graph to complete the sentence. To the nearest 100, the initial amount was, if you look at the graph, you can see the initial amount at week 0 was $200. All right, then it says identify the slope. So that's going to be your difference in y's over your difference in x's. So you can see that you're given 2 points. So that would be 1140 and 576 and 20 and 8. So we've done slope before, and you can see they've just plugged these numbers in and simplified. They got the slope of 47. All right, it says what are the units of the slope and how does the slope relate to this scenario? So this is the amount. The difference in y's is the difference in the amount in the savings account, and the difference in x's, or t in this case, is time in weeks. So that would be your difference in weeks. All right, substitute into point slope form and write. So they've substituted the 8 and the 576 as one of your points. They've used the distributive property to distribute the 47 and get rid of the parentheses, and then added 576 to the other side. After substituting in the equation, use the distributive property, and that gets rid of your parentheses here. All right, so it says the initial amount was at T0. So we can check that. You can see up here, T is in time. At T0, that's when your initial amount occurred. All right, that's task 4. If you have any questions, please let me know.